So hi guys, I'm Lynn here from the Dublin Academy. I'm a chemistry teacher here in the Dublin Academy of Education. So for today's fifth year chemistry lesson, we're going to continue on having a look at oxidation and reduction. So for those of you in my day school class, we started to have a look at this in our previous lesson last week, and I set you a few questions to have a look at the end of our last video. So I'm going to start off today by having a look at those and we'll correct them together. So this is on page 60 of the notes if you want to have that open in front of you. I hope you all got those questions done and we'll have a look at them now together. So these are short questions from question 4 of the exam. They're all higher level Leaving Cert questions, and we have 5 different ones to have a look at here, and I have them on the board behind me. So the first one we're having a look at is from 2017. As I said, it's a 6-mark question from that particular year, question 4. And what we're trying to do here is we are trying to assign the oxidation numbers, okay? So we were talking about the rules that we use to assign these oxidation numbers in our previous lesson. So this will be a little recap of that as well. So if we look at the first one here, OF2. And now we need to think back to the rules that we went through in our previous lesson, and you can refer to those in the notes as I'm talking. Now, what we see here is we have oxygen, okay, and we also have fluorine. And if we look through our rules, we see that there are 2 rules that we can use here in this particular example. So oxygen normally has an oxidation number of -2. Now, in this particular example, it's bonded to fluorine. Fluorine is one of the halogens, therefore it's going to have an oxidation number of -1. Okay, the halogens are in group 7. They're trying to gain that extra electron to have a full outer energy level. So fluorine has an oxidation number of -1. Now, when we add the oxidation numbers together in a molecule, they should equal 0. So that's one of our rules. The sum of the oxidation numbers in a molecule should equal 0. And we see it, we have a bit of a problem here, because if oxygen is normally -2 and fluorine is -1, that doesn't add up, okay? And the reason for this is because this is one of our exceptions. So we did discuss this in our previous class. Fluorine is a lot more electronegative than oxygen, okay? So they're both of these elements like to gain electrons, but fluorine is better at it than oxygen is. It's more electronegative. And remember, you can refer to those electronegativity values. They're in your formula tables book if you can't remember those, but it's there for you. You don't need to learn any of them off. But if you refer to those values, you see that fluorine is more electronegative. In fact, it's the most electronegative element on the periodic table. So as a result of that, it's pulling the electrons away from the oxygen. So fluorine here will still have its -1 oxidation number, okay? But the oxygen here, instead of being -2, is actually +2. So it's one of our exceptions. It doesn't follow the normal rule, and it's all to do with the fact that fluorine is more electronegative, okay? So our answer here for this, we're asked what the oxidation number of oxygen is. The answer is +2. And as I mentioned previously, do always show the sign as well. If it's a positive or negative number, always put the plus or minus in. So on to our next one, we have XeF4, okay? So again, we have to look through our rules and see what applies to this particular example. And we see again that we've got fluorine here. It's a halogen. It's going to have an oxidation number of -1, okay? Now, none of our oxidation number rules apply to xenon. So we have to try and figure it out, okay? Now remember again, if we add all of the oxidation numbers together, it should equal 0, okay? So it should equal 0. Now we've got fluorine, which is -1, and there are 4 fluorine atoms in this particular molecule. So that's -1 times 4, which is going to be -4. And then I'm just going to call xenon X for the moment, because we don't know what it is. It's the unknown, okay? So of course that means that to add up to 0, xenon has to be +4. Okay, so just write that in over it there. So our answer there for number 2 for this particular question is +4 for xenon. Okay, so moving on then to the next question from 2004 this time. The first example here, we have H2O2. So this is what we call hydrogen peroxide. This is a peroxide molecule. And again, this is one of our exceptions for oxygen. So hydrogen is normally +1, okay, and oxygen is normally -2, Okay, but if we have 2 minus 2's and 2 plus 1's, that does not add up to 0. So we need, again, we see that this is one of our exceptions, okay? So in a peroxide molecule, oxygen is not minus 2, it's only minus 1. And that's another one of those exceptions for oxygen that you need to make sure you remember, because they do appear on the exam very frequently, as we can see here already. There's an exception for oxygen, and here we have a second one, okay? So minus 1 is the oxidation number of oxygen in this particular molecule. On to the number 2 here, KBrO3. Now, we have oxygen here, which is minus 2. Okay, so neither of the exceptions of oxygen apply in this particular case. So we have a minus 2 oxidation number for oxygen. Potassium then. Potassium is in group 1 of the periodic table. It likes to lose 1 electron. Therefore, its oxidation number, when it's in a compound, is plus 1. Okay, so plus 1, and then we have the minus 2 for the oxygen. Now, if we look at bromine, bromine is a halogen. It's found in group 7 of the periodic table. And remember, the halogens like to gain electrons. That's what they're trying to do when they bond. So we would expect the halogens to have a minus 1 oxidation number, okay? But bromine doesn't in this particular case. Again, because of electronegativity values. So bromine is less electronegative than oxygen. So bromine in this case is bonded to something that is more electronegative than it, so it's able to attract electrons better. The oxygen's able to attract electrons better than the bromine, okay? So to work out the oxidation number, again, we just use a very simple little algebra equation, okay? So we've got the plus 1 for the potassium. I'm just going to call the bromine X for the moment because we don't know. Minus 6 equals 0, okay? So plus 1 minus 6, okay? So that's minus 5 equals 0. So X equals plus 5. So our bromine in this particular molecule is plus 5, okay? So you can just, as I said, just construct these simple little algebraic equations to help you figure out unknown oxidation numbers, because we don't have a situation where our rules will apply to every single atom in the molecule, okay? So on to our last example from 2002. We actually had a look at this one in our previous class, so this was just a little bit of revision for you. So what we're trying to do here is, again, assign our oxidation number. So this is sodium thiosulfate, Na2S2O3. Okay, so our oxygen, minus 2, our normal rule applies here. Sodium is in group 1 of the periodic table, 1 electron in its outer shell, which it's quite happy to lose. Therefore, it has an oxidation number of plus 1. And we need to now figure out what sulfur is, okay? So remember that they should all add up to 0, okay? All of the oxidation numbers of the atoms in this molecule should add up to 0. So plus 1 times 2, okay? Now, we don't know what sulfur is, so I'm going to call it X, but because there are 2 sulfur atoms in this molecule, we have to say 2X, and then minus 6 equals 0, okay? So we're trying to solve for X. We want to know what sulfur's oxidation number is in this particular molecule. So plus 2 plus 2X minus 6 equals 0, okay? So that's going to be 2X equals 6 minus 2. So 2X equals 4. Therefore, X is going to be plus 2, okay? So sulfur, each of those sulfur atoms has an oxidation number of plus 2. All right, so we've gone through those 5 different examples there. That would be very typical of the kind of thing you could be asked. And as I said, each one of these questions is worth 6 marks, okay? So can I get you now just to turn back, please, in your notes to page 47, okay? So page 47 of your notes. So what we're going to have a look at now is we're going to have a look at how oxidation numbers can change during a reaction. Okay, so we've talked a lot about how we assign oxidation numbers to atoms in a molecule. But what we want to do now is look and see, well, if oxidation numbers change, how can we explain that, and what does that mean for those reactants, for those chemicals that are reacting in this oxidation and reduction reaction. So we're going to look at this chemical reaction that we have here on page 47 of your notes, and we're going to assign our oxidation numbers first. That's the first step here. So we'll just work our way across the balanced equation. So if we look at the first molecule here, HgCl2. So chlorine is in group 7, it's a halogen, therefore it's going to have an oxidation number of -1, okay? So -1 times 2 is -2. So to balance that out, this one has to be, our Hg, our mercury, has to be +2, okay? So +2, -2, therefore the sum of the oxidation numbers in that molecule is now 0, okay? So the same here then, we've got tin and chlorine. So chlorine again is -1 times 2, so the tin has to be +2. Okay, so we move over to the right-hand side of this equation. We have again chlorine, which is -1, so that's going to be -2, but this time we have our mercury, Hg2, okay? So each one of these mercury atoms would be +1, okay? +1 times 2 is +2, -2, therefore the sum again is 0, okay? And then finally here, SnCl4, so our chlorine again is -1, times 4 is -4, so the tin has to be +4, because remember, they have to add up to 0 when we have a neutral molecule, okay? So you're taking each atom into account. Now in the balanced equation, of course, we have this big 2 here. That doesn't come into consideration when we're assigning oxidation numbers. We're just looking at the number of atoms within each molecule, okay? So don't worry about that coefficient for the moment, all right? So what we want to do now is we want to look and see what has changed. What oxidation numbers have gone up? What oxidation numbers have gone down? Okay, so the first thing we see here is that our mercury has gone from +2 to +1. Okay, so +2 to +1. Now, our oxidation number has gone down. And when our oxidation number decreases, that tells us that the substance has been reduced. Okay, now if we think back to what we were discussing with oxidation and reduction in our last lesson, and we remind ourselves of this acronym, oil-rig, okay? So what this means, oxidation involves the loss of electrons, reduction involves the gain of electrons, okay? So this substance's oxidation number has gone down, therefore we can say that it has been reduced. Okay? The number is going down, it's decreasing, and the reason for that is because this substance is gaining electrons. Electrons are negatively charged, therefore as electrons are added, our oxidation number goes down, it becomes more negative, okay? So electrons have been gained here, remember, oil-rig. Okay, so electrons have been gained by this particular substance, and using the oxidation number we can actually tell how many electrons. So to go from +2 to +1, we see that 1 electron is gained. Okay, so 1 electron is gained here in this particular example. All right, so what else has changed? So if we look across our oxidation numbers, we can see here that the tin has gone from +2 to +4, okay? So the oxidation number this time has gone up, okay? It's becoming more positive. Now, if we think about charged atoms and how we can make an atom positively charged, it's to do with the loss of electrons. Remember, electrons are negatively charged, so if an atom loses an electron, it becomes more positive, okay? So this has been oxidized, okay? So +2 to +4, it has been oxidized. We're losing electrons here to become more positive. So sometimes that can be a little bit tricky to remember. Electrons are negative, so if we lose electrons, the atom becomes positive. So +2 to +4, we've lost 2 electrons here. Okay, 2 electrons lost in the process. So we're able to identify, using our oxidation numbers, what has been oxidized and what has been reduced. Okay? Now, the other piece of information that I want to introduce you to here, another key term, okay, is what we describe as an oxidizing agent and a reducing agent. Okay? Now, during a reaction, the reagent that is reduced, which in this case is our HgCl2, okay, so this is reduced during the reaction, it's gaining electrons. this is what we would call the oxidizing agent. Okay, so this is the oxidizing agent. Okay, it is allowing the other reagent to be oxidized. So this is our oxidizing agent. It itself is reduced. It gains electrons. That's an important thing to highlight, the fact that oxidizing agents gain electrons. It's allowing the other substance to be oxidized. So by gaining electrons, it's allowing the other reagent in the reaction to lose electrons. Because remember, these two things happen simultaneously. If we have one species in a reaction losing electrons, something else has to gain electrons. The electrons have to go somewhere, okay? So an oxidizing agent is reduced during a reaction, it gains electrons. The thing that is oxidized during the reaction is described as the reducing agent. Okay, so this is the reducing agent in our reaction. Okay, now a reducing agent is itself oxidized. It's allowing something else during the reaction to be reduced. It's allowing something else to gain electrons. Therefore, it has to lose them. Okay, so it's basically giving away its electrons so that something else during the reaction can be reduced. And those terms are very easily mixed up. So you need to make sure that you've noted that down and highlighted the difference there between your oxidizing agent and your reducing agent. So an oxidizing agent, I'll just repeat it once more, an oxidizing agent is reduced during the reaction, it's gaining electrons. The reducing agent is oxidized during the reaction, losing electrons. Okay, so it's very important that you have that clear in your mind, because as I said, they're very easily confused. Okay, so do just make sure you're clear on that. Okay, so what we're going to have a look at now, we're going to move on to the next part of this topic, and we're going to have a look at balancing redox equations. Okay, so this is on the next page of your notes, so we're on page 48 of your notes. And on page 48 of your notes, I have a full worked example of how to do this. So we've discussed balancing equations before. We looked at balancing equations in terms of the number of atoms at the start of the reaction and at the end. So what we're going to be doing here with these is we're going to not only be balancing the number of atoms, but we're going to have a look at the number of electrons moving around, okay? And make sure that those electrons are balanced on either side of our equation, okay? So, as I said, you have this example in full in your notes on page 48, but I'm just going to work through it here on the board and talk you through each of the steps involved. Okay, so we're going to have a look at this particular example here. So we've got MnO4 minus plus H2S plus H plus gives us Mn2 plus S and H2O. Okay, so what we're going to try and do here is we're going to try and balance this equation. Okay, and as I said, that involves making sure that the electrons are balanced so that we have the correct number of electrons being lost and gained, and also that we have the correct number of atoms on each side. Okay, so we can see immediately that this is not balanced. We can see straight away, like we've got more oxygen on the left than we do on the right. We have more hydrogen on the left than we do on the right. So we have more hydrogen on the left than we do on the right, and so on. So we can see immediately that it's not balanced. So we've got a bit of work to do here. So on page 48 of your notes, I've given you a step-by-step set of instructions as to how to do this. So I'm going to work my way through this now, and you can just follow along, because as I said, you have this in your notes in full. So the first thing we need to do, and we've had a bit of practice of this already, we need to assign our oxidation numbers, okay? So let's start off. So if we move over here, first of all, we start from the left and work our way across. Oxygen is -2, okay? Now, in this ion, okay, this is a group ion. So the sum of the oxidation numbers here need to add up to the charge on that group ion, which is -1 in this particular case. So -2 times 4 is -8. Okay, and remember, we want this to equal -1 over all. We don't know what the manganese is. So just by rearranging that, we can see that the manganese has to be +7, okay, +7. Now, H2S, so hydrogen is +1, therefore the sulfur has to be -2. There's no charge on this. This is a molecule, a neutral molecule, so the hydrogens are going to be +1 each. The sulfur then has to be -1 so that they add up to 0. Okay, +1 times 2 minus 2 is 0. Now this is a simple ion, meaning it's just one charged atom. So this is +1, okay? Again, another simple ion here, so the oxidation number matches the charge, so it's going to be +2. Sulfur on its own, if we think back to rule number 1, this is a free element, so it's going to be 0. Then here we have -2 for the oxygen, and then +1 times 2 for the hydrogen. So again, that would add up to 0, okay? So we've assigned our oxidation numbers the whole way across here. And just as we did in the example a couple of minutes ago, we're now going to have a look and see what has changed. What has gone up, what has gone down? What has been oxidized, what has been reduced? Okay, so we see straight away that this has gone from +7, our permanganate has gone from +7, or the manganese in that group ion has gone from +7 to +2, okay? Therefore, this has been reduced, okay? It has been reduced. It has gained electrons. Now, to go from +7 to +2, we know that it has gained 5 electrons, okay? 5 electrons gained. Now, what else has changed? Well, we see here that our sulfur has gone from -2 to 0. -2 to 0, okay? So that has gone up in oxidation number. We're becoming more positive. So going from -2 to -1 to 0. So we know that this has been oxidized. So electrons have been lost. Now, how many electrons? We've lost 2 electrons, okay? So 2 electrons are lost. So that's the first stage of this, and we've got a lot of marks for doing this already. Assigning our oxidation numbers, figuring out what has been oxidized and what has been reduced. The next thing that we need to do is we need to now take out our oxidation and our reduction equations. So we separate them out from the main equation. Okay, so I'm going to rewrite them as separate equations on their own. We describe these as half equations. Okay, now I'm going to start with the reduction reaction. So we have MnO4 minus plus 5 electrons gives us Mn2 plus. Okay, then we have our oxidation, so H2S minus 2 electrons. Okay, gives us S over here on the right hand side. Okay, so this is our reduction, this is our oxidation. Reduction and oxidation. Now, we need to get these electrons to balance. We can't have a situation where something is gaining 5 electrons, but the other thing is only losing 2. That doesn't work, okay? We have to have the same number of electrons being lost and gained, okay? So we treat this like a simultaneous equation, just like you would in maths, okay? We want to get these electrons to cancel. We need the same number of electrons moving in either direction. So we're going to multiply the top line by 2 and the bottom line by 5. Okay, the top line by 2 and the bottom line by 5. So if I put a 2 there, okay, to multiply that by 2, I'm going to change this 5 now to 10, okay, and I'm going to put a 2 in front of the Mn2 plus. On the bottom line then, a 5 here. Again, this minus 2 times 5 will be 10 electrons, and then I'm going to put another 5 here. Okay, so we've just treated it like a simultaneous equation, and we've multiplied across so that we have the same number of electrons moving in either direction. And because of that now, when I add these 2 lines back together, the electrons will cancel out and I have balanced it in terms of the number of electrons. Okay. What we do now is we take these new coefficients, so by coefficient I mean the numbers in front, okay? We take these new coefficients and we put them back into our original equation. So I basically rewrite the original equation with these new numbers included, okay? So I'm just going to move over here just to have a little bit more space. I'm going to rewrite that equation with these new coefficients, okay? So we have 2 MnO4 minus plus 5H2S plus H plus gives us 2Mn2 plus 5S plus H2O. Okay, now we've balanced our electrons, but we can still see that we don't have the correct number of atoms on either side, okay? So we need to, on the left-hand side and on the right-hand side, write out how many of each type of atom we have, okay? So we have, on the left-hand side, we see that we have 2 manganese, okay? We have 8 oxygens. We have 10 plus 1, 11 hydrogens, 5 times 2 plus 1, and then we have 5 sulfurs, okay? On the right-hand side, 2 manganese, 1 oxygen, we have 2 hydrogens, and we have 5 sulfurs, okay? So we need to get these to balance. We need to get these to balance out. We need to have the same number of atoms on either side, okay? So the first thing we could do, if we have a look at the oxygen first of all, okay? We need to have 8 oxygens on the right-hand side. At the moment, we only have 1. So I'm going to put an 8 here on the right-hand side, and that will then change this oxygen to 8. But of course, it also changes the number of hydrogens. So we now have 16 hydrogens on the right-hand side. 16 hydrogens on the right. So we need to now go back over to the left-hand side to correct that. So at the moment we have 5 times 2 is 10 here, okay, plus the 1 which is 11, but we need 16, we need 5 more, okay? Now a very common thing for students to say is, well, let's put a 5 in front of this, but that would actually only be 15 in total. So what we actually need to do is put a 6 here, okay, to include the one we already had plus an additional 5. So that then will be 5 times 2 is 10 plus 6, which is 16. And now we have balanced our equation. We have the correct number of electrons moving in either direction, lost and gained, and we have the correct number of atoms on either side. Okay, thank you.